Look up on a quiet night, and the sky seems still, eternal, yet every point of light is rushing away. Galaxies flee faster the farther they are. Space itself stretches, and the map of everything keeps changing. But if the universe is growing, where is it going? Into what? The question sounds simple, yet it breaks the limits of ordinary thought. Scientists have chased it through mountaintop observatories, deep space telescopes, even instruments that feel ripples in spacetime itself, and still the answer slips and bends. This film invites you into that mystery, a journey from the first cosmic light to the edges we cannot cross, from ancient starlight to future darkness. Along the way, you'll see how humans, small and curious, keep building meaning against an expanding, centerless sea. It begins with a single person standing alone under the night sky. Somewhere far from towns and lights, where the air feels older and the ground seems to hold memory, the desert breathes in long, slow gusts, and the sand carries the faint scent of sage. Overhead, the sky is sharp and cold and impossibly full. Thousands of stars scatter across the darkness. Some bright and familiar, like Vega and Betelgeuse, others faint and trembling on the edge of sight. The Milky Way spills its pale arc across everything, a soft river of ancient light that seems close enough to touch. In that quiet place, the silence becomes a hum. The person lifts their face and tries to grasp what is really happening up there. Those stars are not fixed. They are not still. Each one, each distant island of fire and dust, is slipping away. This realization does not come all at once. It is a thought shaped by years of people measuring, arguing, watching through glass and steel tubes pointed into the cold. Edwin Hubble once stood on Mount Wilson in the 1920s, staring at photographic plates that showed faint smudges turning into entire galaxies. He noticed that their light was stretched, sliding toward the red part of the spectrum, a soft but clear signature that they were moving away. That night in the desert, the person under the stars might not know all the mathematics, but the wonder is the same. Those points of light are not just there. They are fleeing, and the blackness between them is not empty. It is stretching. The human heartbeat under that sky begins to quicken. If everything is moving apart, if space itself is swelling like dough left to rise, what is it swelling into? The question is both simple and crushing. It seems to ask for a picture. A balloon inside a bigger room. An explosion inside some larger air. But there is no room. There is no larger air. The universe is all of it. And yet it grows. How can everything expand without a place to go? The desert night helps the question settle. The cold air moves against the skin, and there is a sense of scale, the quiet crunch of boots on sand, the far bark of a coyote. The sweep of a telescope dome somewhere miles away, turning with motors so soft they barely whisper. Those telescopes, Keck in Hawaii, Palomar in California, VLT in Chile, all chase the same puzzle, gathering light that has traveled millions, sometimes billions of years just to reach us. That light carries messages about where and when it left. Some of the galaxies that send it are long gone or changed beyond recognition by the time their glow reaches Earth. Still, the signal arrives, faint but true. The space between is getting bigger. One might remember how this became more than theory. In 1964, two radio engineers, Arno Penzias and Robert Wilson, worked on a strange horn antenna in Holmdel, New Jersey. They tried to rid it of an irritating hiss. They scrubbed away pigeon droppings, checked cables, recalibrated circuits, but the hiss stayed. It turned out to be the oldest sound we can hear, the leftover echo of the Big Bang itself, the cosmic microwave background. Proof that the universe was once packed into something unimaginably dense and hot and has been stretching ever since. That discovery stitched human ears to the birth of everything standing in the desert. One can think of that how a faint noise and a bit of static told us we live inside a growing fabric. The thought is dizzying. The stars above look calm, but their calm is an illusion born of distance and time. They are rushing, whole galaxies carried away as if on invisible rivers. The idea of an edge returns, stubborn and childlike. Surely there must be an outside, a border beyond which there is something else. But every attempt to picture it crumbles. The universe is not an explosion into pre-existing blackness. It is an expansion of the blackness itself. The watcher shifts, maybe pulls a jacket tighter against the chill. Even now, new tools like the James Webb Space Telescope float far above Earth, seeing back toward the first stars and the first galaxies that lit up the dark. Their images show delicate spirals and glowing knots so far away that their light left when dinosaurs still walked here, and all of them drift farther as the seconds pass. Yet in the middle of all that motion, the human figure remains still. The desert smells of dust and cold iron, and the stars do not flicker. They burn steady and ancient. The question into what is not solved. But it is alive, breathing in the chest of anyone who dares to look up long enough. To know the universe is expanding is one thing. To feel the weight of that truth under the sweep of the real sky is something else entirely. The edges of thought stretch just as space does, into places where no clear answers wait, only deeper wonder and the faint, thrilling sense that we are riding inside a mystery still unfolding. In the early summer of 1964, two young radio engineers stood beside a curious white horn-shaped antenna rising out of a field in Holmdel, New Jersey. Arno Penzias and Robert Wilson worked for Bell Telephone Laboratories, not as cosmologists chasing the origins of everything, but as practical men improving satellite communications. The device they tended was no ordinary radio receiver. It was a vast, gleaming instrument with a mouth 30 feet long and painted to withstand the weather, meant to catch faint signals bouncing off echo. An early communications balloon, orbiting Earth, day after day. They listened for whispers from space, the sort of faint radio noise that could spoil transmissions. And they tried to account for every possible source of interference. Yet something would not go away. Through the static and mechanical hum, there was a persistent hiss, steady and soft, but impossible to ignore. It did not rise and fall with the sun. It did not disappear at night. It did not shift as they turned the great horn across the sky. They checked and rechecked the electronics, replaced cables, and cooled the receiver with liquid helium to reduce its own noise. The hiss remained. They even climbed inside the vast curved throat of the antenna and scraped away what they politely called white dielectric material, a polite engineer's phrase for pigeon droppings, suspecting that the birds roosting there might have introduced some strange contamination. Clean and gleaming, the instrument still hummed with the same low murmur. At first it was only an annoyance. Wilson and Penzias had no reason to suspect the signal was anything extraordinary. But across the country, at Princeton University, a small group of physicists, led by Robert Dicke, had been wrestling with a theoretical problem. Dicke and his colleagues believed that if the universe really began as a dense, hot fireball, then after billions of years, it should still be filled with a ghostly afterglow. Radiation cooled and stretched by the expansion of space, but not gone entirely. They had been designing their own experiment to hunt for that faint light from creation's dawn, when word drifted to the Princeton group that engineers in Holmdel had stumbled on a persistent hiss that no amount of cleaning or calibration could erase. The connection was immediate. Dicke, upon hearing the news, is said to have turned to his team and remarked, "Well, boys, we've been scooped." In that moment, the practical work of telephone scientists collided with the deepest questions of cosmology. The radiation Penzias and Wilson found was not a nuisance after all. It was the oldest light we have ever seen, the cosmic microwave background. Born when the universe was just 380,000 years old, a mere blink compared to its present age of 13.8 billion years, this glow was once a blinding white-hot sea of energy. But as the universe swelled, space itself stretching, the light cooled and lengthened into the invisible microwaves that bathed their horn antenna. The discovery was quietly dramatic, published without grand headlines. It was simply reported in 1965 in the Astrophysical Journal Letters, a short technical note describing excess antenna temperature at a wavelength of 7 centimeters. Yet behind the dry phrasing, a profound confirmation stood. For decades, scientists had argued about whether the universe had always existed or whether it began in a single violent event. The detection of the cosmic microwave background tipped the scales. decisively toward a hot beginning, what would soon be known as the Big Bang. For the first time, humanity could touch, however faintly, the aftershock of creation itself. The light carried a perfect black body spectrum, exactly what would be expected if it came from a once fiery, dense universe now cooled by expansion. It was as if the cosmos still whispered about its own birth. And two engineers, simply trying to improve long-distance communication, had stumbled onto the Echo Dot in Holmdal that summer. The field around the antenna buzzed with mosquitoes and heat, yet the signal persisted with cosmic patience. Neither Penzias nor Wilson set out to answer what the universe expands into or how it began. They were men with notebooks and instruments trying to remove every scrap of noise from a system. But their noise turned out to be the oldest story of all. With this faint hiss confirmed, new maps would be drawn. In the decades that followed, satellites like COBE in 1989, then WMAP, and later Planck, traced the microwave glow across the entire sky with exquisite detail, turning what Penzias and Wilson first heard as formless static into a speckled portrait of the young universe. Those maps showed minute temperature differences, ripples no larger than a few parts in 100,000, seeds from which galaxies and clusters would grow. But in 1964, none of that was yet known. All that existed was a quiet signal no one could wish away. Imagine standing by the Great Horn one warm evening, the grass around your boots alive with crickets, the aluminum shining pale under a dim New Jersey moon. You know you have scrubbed and tested, you have done everything right, and still the sky itself will not fall silent. Then, through conversation and shared curiosity, you learn the hiss may be the universe's first breath stretched across time. Suddenly, the night around you deepens. The air seems older. The stars overhead feel less like distant lamps and more bright, like traces left by an expanding fire that has never truly ended. That faint glow, unseen by eyes but caught by patient machines, changed our place in the story. It told us the universe did not simply exist. It began, it evolved, and it is still moving, still stretching the fabric of space even now. What was once an engineer's puzzle became a key to understanding the living history of everything. And though it came without fanfare, that quiet discovery remains one of the most profound human moments, a whisper from the beginning. Found while chasing a better telephone signal, high in the San Gabriel Mountains of California, the air turns thin and sharp as the road winds upward, toward a white dome that gleams against the sky. In the 1920s, this was one of the most remote places in American science, reached by steep switchbacks and hours of patient driving on dirt and gravel, the night air crisp and full of pine. Here stood the 100-inch Hooker telescope at Mount Wilson Observatory, the largest in the world at the time. A machine built not just of steel and glass, but of hope that human eyes could push deeper into the dark than ever before. It was here that Edwin Hubble, a tall man with a calm, almost private manner, would spend long, cold nights alone, guiding that massive instrument to collect the faintest smudges of light the sky could offer. In those years, the universe was thought to be far smaller than we know now. Many astronomers believed that everything, the spiral and elliptical clouds seen through telescopes, was contained inside the Milky Way. They called them nebulae. Unsure whether they were new star clusters forming nearby or something else entirely. Hubble, with his meticulous patience, began to measure the light from these fuzzy shapes. He studied variable stars, especially Cepheid variables, whose regular brightening and dimming could be used as a kind of cosmic yardstick, thanks to the work of Henrietta Swan Leavitt a decade earlier at Harvard. Her discovery that the period of a Cephid's pulse is linked to its true brightness gave astronomers, for the first time, a way to measure vast distances. Hubble applied that knowledge with deliberate care. Night after night, he took photographic plates, guiding the Hooker by hand, sometimes for hours, to capture enough light for a single frame. In 1923, he found Cepheid stars in the Andromeda Nebula, proving beyond argument that it was not a mist inside our galaxy, but an island universe millions of light-years away. The scale of reality began to stretch. If Andromeda lay outside the Milky Way, then the universe was not just bigger, but unimaginably so. Yet the deeper shock came a few years later. As Hubble compared the distances he was calculating with the spectral fingerprints of those galaxies' light. Astronomers like Vesto Melvin Slipher had already noticed that the lines in these spectra-thin bands, marking the chemical makeup of stars, were shifted toward the red end, a sign that the sources were moving away. Hubble began to gather these redshift measurements, pairing them with his new distance calculations. Slowly, a pattern took shape in his worn notebooks. The farther a galaxy lay, the faster it seemed to be receding. By 1929, Hubble had enough data to plot something extraordinary. On the chalkboard in his office and in his field notes, he drew a simple graph, distances on one axis and velocities on the other. Instead of a scatter of random points, a line emerged almost straight, rising as it went. It meant that the universe was not static. It was expanding, galaxies fleeing from one another in every direction. It was not an explosion with a single center flinging matter outward into empty space. It was space itself stretching every part from every other part. Like dots on the surface of an inflating balloon, imagine him there on the mountain. A solitary figure in the glow of a desk lamp, holding a glass photographic plate to the light and marking tiny smears of silver. His notes yellowed with time now, record numbers that turned human understanding upside down. The universe had no fixed stage. The stage itself was alive, changing and restless. The impact rippled slowly at first. Albert Einstein, who had reluctantly introduced a cosmological constant to keep his equations from implying expansion, came to visit Mount Wilson in 1931, walking the grounds with Hubble. He is said to have admitted regret for resisting what the data showed, calling the constant his biggest blunder. Astronomers across the world re-examined their maps and assumptions. The sky was no longer a calm dome, but a living, dynamic fabric. For those who handle data every night, revelation can be quiet. There were no shouts on that mountain, no wild celebrations. Instead, there was the silent weight of new truth pressing in, the slow turning of a mind adjusting to the unimaginable. The Milky Way was just one of countless galaxies. The universe was not fixed, but swelling. And if it was expanding, then perhaps it had once been smaller, denser, hotter, a seed of everything. Even now, nearly a century later, the echo of that realization reaches anyone who looks at Hubble's original plots. Faint pencil marks, careful and human, describe a motion so vast it outpaces language. The Hooker telescope still stands at Mount Wilson, its great gears and glass relics of an era when a single man could change the cosmic map with quiet persistence. And the night sky above that mountain remains cold and endless, yet not still. Its light still stretches, carrying the story Hubble uncovered into the future. To picture that moment is to feel a strange closeness with the past. A man alone with his calculations, a graph line tilting upward. A universe quietly expanding beyond anything the human heart had imagined. Without fireworks or trumpet calls, Edwin Hubble's work widened reality itself and prepared the ground for every modern quest to know what we inhabit, what we move through, and perhaps one day, what it all is expanding into. It is almost impossible to imagine the universe growing because there is nothing in ordinary life quite like it. Yet for almost a century, scientists have reached for household things to help people picture what is happening on the largest stage imaginable. One of the most familiar images begins with a balloon. You take a marker and draw a few dots on its surface, each one standing in for a galaxy. As the balloon is slowly filled with air, the dots all move away from one another. None privileged as the center because the surface has no special point. Every sees the others receding. Another picture sometimes used is a pan of bread dough left on a warm counter, raisins scattered through it like star systems. As the dough swells, each raisin finds its neighbors sliding farther away, though none of them are moving by their own power. The dough itself is stretching, carrying them apart. These pictures are useful, especially for someone just beginning to think about an expanding universe. They are physical, familiar, and they offer one vital correction to a common mistake. Expansion is not about galaxies hurling themselves through empty space, like bullets fired outward from a single origin point. Instead, It is about space itself enlarging, carrying the galaxies with it. Yet as clear as these analogies feel at first, they are also quietly misleading. The balloon is an object in a larger room, its surface swelling into surrounding air. The bread sits on a countertop, its dough rising into the kitchen. When we talk about the cosmos, there is no outside room and no surrounding air. The fabric of space does not push into anything. It simply becomes larger. That is where ordinary experience falters. In the 1930s and 1940s, teachers and writers leaned heavily on the balloon because it so nicely avoided giving any galaxy a privileged center. The surface has no edge. Walk long enough in any direction, and you return to where you began, as sailors do on the globe of Earth, but even that surface is two-dimensional. While the real universe is three-dimensional at minimum and perhaps far more complex, worse, a balloon's expansion depends on some inner pressure and an outer environment, while cosmic growth has neither. Space does not need to shove aside other space or climb into a greater void. It is all there is. The raisin bread works in a different way, letting one imagine three dimensions more easily than a balloon skin can. Yet dough has a crust, a boundary where the expansion stops. And the raisins themselves are embedded in the substance of the dough. Galaxies are not sitting inside some tangible medium. They are part of the geometry itself, and dough rises into the air around it. Space does not have air around it. There is simply no container. This is where the mind begins to bend a little, because human language has been built for kitchens and hillsides and seas, not for self-stretching spacetime. Even scientists speak cautiously, often substituting the phrase metric expansion for the harder idea that the intervals between points grow because the geometry underlying them changes. When Edwin Hubble traced his redshift relation in 1929, he did not claim to know what the universe was expanding into. He simply showed that the light told us distances themselves were stretching. Later, Albert Einstein's general relativity gave the mathematical foundation. The equations of the cosmos do not require an outside. They describe how the distances can change within the whole itself. To sit with this is strange. It is easier sometimes to return to the balloon because the picture feels safe. Teachers will warn, though not to think about the balloon floating in a room. Imagine only its skin. Ignore the air beyond, and forget the hand that blows it up. Still, it is hard. People are built to think of edges and surroundings. Even the night sky, which feels endless, is always framed by the horizon. Astronomers have spent decades trying to find ways to talk about this without betraying the physics. The cosmic microwave background discovered by Penzias and Wilson gave the first powerful proof that the universe once occupied a hotter, denser state. Later satellites such as COBE in 1989 and WMAP in 2001 mapped that faint radiation across the whole sky, showing that expansion is not a story we made up but one written in ancient light. These maps reveal no boundary. The data say nothing about a container. They speak only of distances changing and wavelengths stretching. When a modern cosmologist stands in front of a class and explains, they often pause and confess that analogies are crutches. They help you climb a little way and then fail, because our world is too small to hold the real thing. The universe is not an inflating balloon inside a larger void. It is all there is, and its expansion is the simple, difficult fact that the metric itself, the ruler by which we measure, changes with time. Picture again the night sky. Imagine you could pin two galaxies with invisible threads and mark the distance between them. Over millions of years, those marks would drift apart. It's not because the galaxies are sailing through emptiness, but because the threads themselves lengthen. There is no shore to aim for, no outside to enter. Space is stretching not into something else, but into itself. This subtle difference matters because it frames how we ask questions. If we demand an into what, we might be forcing a kitchen image onto a cosmic reality that refuses to fit. What we know is enough to amaze. Light from Andromeda still travels to us, redder than it was when it left. Quasars blaze at the edge of our vision, carried farther away each moment. The faint afterglow of the Big Bang still cools as space grows. The expansion is real, but it does not need a surrounding field. It only needs the fabric we already inhabit, endlessly reshaping. And though we can sketch balloons and bread to begin the journey, sooner or later we have to set them down and let the strangeness stand bare. Accepting that our universe can grow without growing into anything at all, far above the turning Earth, where the air thins away to nothing and the sky hardens into black. A small craft once drifted with its great sensors open, listening for the oldest light there is. In November of 1989, NASA launched the Cosmic Background Explorer COBE, a modest, boxy satellite with gold foil and long cooling booms, designed not for glamour, but for precision. Its mission was simple and audacious at once: to take the faint hiss that Penzias and Wilson had stumbled on in 1964 and map it. To transform a single haunting whisper into a picture of the infant universe itself. Up until that point, the cosmic microwave background was known to exist, but it seemed bland and featureless, almost perfectly smooth, as if the early cosmos had been utterly uniform. Yet for galaxies, stars, and people to form, there had to have been some slight irregularities. Tiny wrinkles where matter clumped and gravity could one day draw it tighter. COBE carried instruments cooled to cryogenic temperatures, so sensitive that even a slight warmth from the satellite could spoil the measurements. It spent years scanning the sky, spinning slowly, building up a full sky map of microwave radiation, pixel by pixel, like an ancient cartographer charting unknown seas. In 1992, when the team finally revealed the results, the scientific world fell quiet for a moment. Spread across a globe of false color were patches of slightly warmer and cooler radiation. Differences no greater than 1 part in 100,000, but enough to seed every galaxy, every cluster, every world. Stephen Hawking, not given to careless praise, called it the discovery of the century. If not of all time, for the first time humanity saw a baby picture of everything. A snapshot of the universe just 380,000 years after the Big Bang. When it had cooled enough for light to travel freely, those faint blotches were more than decoration. They were a blueprint. The warmer regions marked slightly denser zones where gravity would slowly gather gas and dark matter, coaxing the birth of stars and the spiraling forms of galaxies. The cooler parts would become the great voids. Immense expanses almost empty. In that unevenness lay the future cosmic web. But COBE was only a first step. Its resolution was coarse. The map was like looking at Earth through a misted window. Within a few years, the Wilkinson Microwave Anisotropy Probe, WMAP, was planned to sharpen the picture. Launched in 2001 and stationed at a quiet gravitational balance point called L2, 1,000,000 miles from Earth, where the Sun and our planet's poles cancel enough to give stability. WMAP spent 9 years turning slowly and scanning the whole sky. Its data was astonishingly clean. By 2003, scientists had an image of the young universe with clarity, 100 times better than COBE. The tiny ripples now appeared in crisp detail, and from them, cosmologists could extract the universe's age with new precision, 13.7 billion years. They could also weigh its contents about 5% ordinary matter, nearly 25% dark matter, and the rest dark energy. The still mysterious force driving accelerated expansion. WMAP's maps looked like painted eggshells, mottled blue and orange, but inside them were equations as deep as ocean trenches. They told how fast the universe expanded, how curved or flat space might be, and how the first elements formed. These were not just pretty images. They were cosmic ledgers, ancient light turned into numbers. Still, scientists wanted more. The European Space Agency's Planck spacecraft, launched in 2009, took the work to its current peak. With detectors cooled to 1/10 of a degree above absolute zero and mirrors polished to near perfection, Planck swept the sky with exquisite patience. Till 2013, its maps were so sharp that they showed subtle alignments and anomalies. Hints that the early universe might still hold secrets we don't yet understand. Planck revised the age slightly to 13.8 billion years and refined every parameter of the standard cosmological model. The recipe of our cosmos, imagine these craft in orbit. Far beyond weather and radio chatter, their instruments wrapped in black and gold foil. antennas slowly sweeping across the whole celestial sphere. They listened not for stars, but for the dim background glow left when the first atoms formed and light escaped the primal plasma. They moved without drama, silent but for occasional signals sent back to ground stations in Madrid, Canberra, or California. Below them, the earth turned, blue and cloud-streaked. Above them stretched a sky that was not empty, but alive with ancient whispers. A chain was. A pair of engineers cleaning pigeon droppings on an antenna began the story. Decades later, small teams built machines of almost absurd delicacy to measure temperatures colder than deep space itself. The result is a picture that fits on a screen yet holds the weight of all existence, a baby universe, modeled and imperfect in exactly the right way for us to be here. When you look at those maps, false-colored though they are, you are seeing beyond every star and galaxy, beyond every atom that would one day form planets and cities. You are looking at a wall of light so ancient it comes from a time when there were no stars, no dust, just hydrogen and helium beginning to settle. The cold and hot spots are not storms or clouds, but the first fingerprints of gravity and time. From Cobbe's grainy oval, to WMAP's intricate egg, to Planck's final masterpiece. The view has sharpened, but the essential wonder remains. We can now trace the shape of the cosmos itself, not by sailing its edge, but by listening to the light left from its birth. The maps have no boundary line, no place where space stops and something else begins. They wrap around us completely, reminding us that we are inside, not outside, part of the same expanding story they depict. They are as close as we have to a photograph of everything's first dawn, and they whisper with every pixel. How small questions and quiet instruments can reach all the way back to the beginning, in the closing years of the 20th century, when many astronomers believed the great outlines of the cosmos were finally understood. A quiet revolution began with small teams pointing their telescopes toward dying stars and distant galaxies. For decades, the expectation had been simple and reassuring. Ever since the Big Bang, the universe had been expanding. But the pull of gravity, though weak across vast gulfs, should still be slowing that expansion down. Like a ball tossed upward, space might keep growing for a time, but would eventually decelerate. Perhaps it would coast forever at a diminishing rate. Perhaps one day it might even reverse, collapsing in a long distant future known as the Big Crunch. No one doubted that gravity, the great shaper of galaxies and stars, would at least resist the outward push begun at the birth of everything. Into that climate came a new way of measuring the universe's pace. A special kind of exploding star, a type Ia supernova, burns with a consistent brightness because it comes from a white dwarf star pushed past a critical mass. These events, rare but unimaginably luminous, can outshine entire galaxies for a brief time. And because their peak brightness is understood, astronomers can use them as standard candles, cosmic beacons, whose apparent faintness tells how far away they are. By combining their distance with how much their light has been stretched, redshifted, by the expansion of space, one can plot how quickly the universe has been changing in the early 1990s. Two separate groups set out to map this with an ambition few outside astronomy noticed at first. One team, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and another, the High Seas Supernova Search Team, led by Brian Schmidt of Australia's Mount Stromlo Observatory and Adam Rees at Johns Hopkins University, began hunting these stellar detonations at staggering distances. They combed through photographic plates and early digital sky surveys, developed software to catch faint flickers that might betray a new supernova, and raced to get spectra before the light faded. It was painstaking work. Nights on mountaintops in Chile and Hawaii, days spent coordinating telescope time from Keck, Cerro Tololo, and the Hubble Space Telescope. Supernova do not announce themselves politely. They bloom and fade, and catching them at the right moment is like chasing lightning with a net. But slowly, data points accumulated, and when the teams plotted their findings in the mid-1990s, the curves refused to follow expectation. Instead of a gentle, Deceleration under gravity's steady hand, the expansion seemed to be speeding up. The more distant the supernova, meaning the further back in time, their light was born, the slower the expansion had been than compared to now. Space was not coasting. It was accelerating. Something unseen was driving galaxies apart faster and faster, as though an invisible, repulsive force had begun to dominate on the largest scales. When the teams compared notes and results in 1998, the shock was profound. Centuries of physics had taught that gravity pulls, mass attracts, and the universe ought to slow. Yet the data, drawn from dozens of brilliant stellar deaths, scattered across billions of light years, said otherwise. The term dark energy was adopted not because anyone understood it, but because language needed a placeholder for this unseen pressure woven into the fabric of space. Some linked it to Einstein's old cosmological constant, the term he once added and then rejected in his equations of general relativity, intended to hold the universe static. Perhaps his biggest blunder had been prescient after all, in offices and observatories. The mood shifted from quiet confidence to a deep, almost disorienting humility. The cosmic microwave background had given a picture of the early universe and suggested its content. But now came a force no one had accounted for, a form of energy making up roughly 70% of the cosmos. Exerting a negative pressure that pushed space to expand faster and faster, it was as if an ancient engine had switched on long after the Big Bang, or perhaps had always been there. Hidden in the equations but overlooked, you can picture the moment a little. A researcher late at night in front of a flickering computer screen, the plots appearing one by one, each supernova, a tiny point with error bars like gossamer threads, the line of best fit bending the wrong way. Perhaps coffee cooling beside a keyboard, a silence settling heavier with each click, somewhere in Berkeley, somewhere in Canberra, somewhere in Baltimore. The same realization spreading, the universe was not headed toward quiet coasting. It was running away from itself faster with time. The announcement reached the broader world quietly at first, then with growing astonishment. Newspapers in early 1998 carried brief articles, but within months the story deepened. Most of the universe is not stars, not planets. Not even the mysterious dark matter hinted at by Vera Rubin's galaxy rotation curves decades earlier. But something stranger still. A new cosmic majority had been uncovered by observing faint stellar embers at the edge of vision. Since then, dark energy has remained a riddle wrapped in equations. We measure its effect, the accelerating expansion confirmed by ever more refined surveys. Space missions like ESAS, Euclid, and NASA's Roman telescope, preparing to probe it further, yet its nature is unknown. Is it a constant energy density of space itself? A dynamic field that changes over time? A clue that general relativity breaks at vast scales? No answer has yet replaced the mystery. What those nights in the 1990s did give, however, is a permanent shift in the human map of reality. The known universe grew stranger and vaster in an instant, its fate rewriting itself on a handful of graphs and camera plates. Instead of a cosmos slowing gracefully, perhaps preparing one day to fold back, we inhabit one racing faster into cold and isolation. Driven by an unseen presence that fills the void with restless push, and it all began with the quiet light of dying suns, caught just in time before they vanished, telling us across unimaginable distances that what we thought was safe knowledge about the future of everything was only a prelude to deeper unknowns. If you travel far enough in one direction, where would you end up? It is a question older than science itself, born whenever someone looked across a flat plain or stood on a ship deck and watched the horizon slide forward, promising an end that never arrives. For centuries, people pictured the cosmos as something with edges, the firmament of medieval maps. The crystalline spheres of Aristotle, or later the vast but bounded shell, imagined by some early astronomers. It seems natural to ask where space stops and what lies beyond. Yet when the modern universe revealed its expanding nature, that question began to collapse under its own assumptions. Perhaps there is no outside at all. Perhaps the universe is everything. An edge is a word with no place in the conversation. This is difficult to feel because our daily world is full of boundaries. We walk through doors. We watch rivers meet the sea. We see sky end at a mountain ridge. Even the balloon and raisin bread images used to describe cosmic expansion smuggle in the idea of an outside. The balloon floats in a room. The dough swells into kitchen air. But in the equations of general relativity, which have guided our cosmic thinking since Einstein published them in 1915, there is no need for space to have an edge or for an outside container. The geometry of the universe can be such that it is finite in extent but without borders, much as the surface of the Earth. It's finite, but you will never fall off it. If you could sail a ship across the ocean forever, ignoring storms and currents, you would eventually return to where you began. The planet's surface is limited yet unbounded. Translating this to 3 dimensions is where human imagination begins to tremble. But the math is sound. Cosmologists describe a closed universe as something like a 3-dimensional sphere. We are tiny creatures inside that hypersphere, unable to step out to see its true form. Just as an ant crawling on Earth's surface cannot see the globe from space, in such a cosmos, if you set out in one direction long enough, ignoring cosmic expansion and practical impossibility, you could in theory return to your starting point. Though the journey might take longer than the age of the universe itself, space curves back on itself. There is no wall. Other models describe space as flat, meaning parallel lines stay parallel, but flat does not guarantee edges either. A flat universe can be infinite, stretching forever in every direction with no boundary. Observations of the cosmic microwave background by Kobe, WMAP, and Planck suggest our universe is astonishingly close to flat. But with room for subtle curvature, we may not have the precision to measure. Infinite, or closed, but boundless. In both pictures, the word edge slips away. What? Then, about the question expanding into what? If space is not sitting in something larger, how can it grow? Here, geometry once again untangles confusion. Think of the surface of a balloon, the 2-dimensional creatures. Living there do not need to know about the 3rd dimension of the air around it to describe their surface expanding. The distances between points grow because the surface itself is stretching. Our 3-dimensional space can do the same without invoking a 4th spatial direction it must push into. The into what is unnecessary. The metric, the ruler built into the fabric of space, simply changes with time. When Edwin Hubble plotted redshifts in 1929 and saw the linear rise between distance and speed, he was not claiming to see an edge. His data said only that farther galaxies recede faster because space between them swells. Later, when Arno Penzias and Robert Wilson caught the ancient light of the Big Bang, they did not find a boundary, only a horizon, the limit of what light has had time to reach us since the beginning. That is an important distinction. The observable universe is like a glowing sphere around. That's about 46 billion light-years in radius, not because beyond that lies a void, but because beyond that, light has not yet arrived. The true cosmos might extend far past this horizon, perhaps endlessly. Still, the human desire for an outside is stubborn. You can imagine standing on a ship's deck under endless sky, knowing Earth's curves but unable to see it. The sea gives no hint of returning to your starting port if you sail on. In space, the effect is deeper. There is no shoreline, no stars that mark an end, only a smooth continuation in every direction. Some nights, scientists working atop Mauna Kea or Cirro Paranal feel this profoundly, the dome of stars, not a ceiling but a vast loop with no door. The concept of a finite yet unbounded universe was introduced as early as 1917, when Einstein wrote his first cosmological model, a closed, static cosmos with positive curvature. Though that model failed once expansion was discovered, the notion of boundaryless space remained. Later observations and theory allowed more complex shapes, toroidal, hyperbolic, but they all share this same idea. You do not need an outside for the inside to grow. Even modern visualizations, such as the Planck satellite's all-sky maps of the cosmic microwave background, reinforce this. The modeled oval images you see are projections of a sphere around us, not a shell edge, but simply the farthest we can observe. Beyond, space continues. though we may never know in what shape or how far. To sit with this is unsettling, but freeing. There is no cliff at the universe's end, no cold black wall, no void waiting beyond. Our cosmos may be infinite, or it may be curved, so that if you traveled forever you could return, a cosmic sailor looping back across unimaginable gulfs. Either way, there is no outside. The universe does not expand into something larger. It is all there is, and its growth is the change of its own fabric, a quiet rewriting of distance itself. For a mind used to shores and fences, this feels strange. Yet under a dark night sky, where the stars lie scattered like distant ships on a boundless sea, the idea begins to feel right. You are afloat with no edge to reach and no beyond to enter. Only an ever-changing ocean of space, carrying everything further, apart while remaining whole, far above the deserts of New Mexico and the dry plateaus of Arizona. Under some of the darkest skies left in North America, a wide white telescope dome turns with patient precision, part of a global effort to chart the universe in detail unimaginable to earlier generations. The Sloan Digital Sky Survey, begun in the late 1990s with a 2.5-meter telescope at Apache Point Observatory, set out to do something humans had never attempted: create a three-dimensional map of the cosmos. Not with a few hundred or even a few thousand galaxies, but with millions, each one marked with its position and how fast it moves away from us. Astronomers loaded enormous glass plates with digital detectors and sent the telescope sweeping across the night, catching faint smudges of light and breaking them apart into spectra so they could measure redshift. The stretching of wavelengths as space expands, the data began to pile up in the early 2000s. Turning computers into cosmic atlases, each galaxy became a tiny dot in a volume of unimaginable size, and slowly a shape emerged. The universe, when seen at this grand scale, is nothing like a random scatter. Instead, it forms something astonishing and almost organic. Long, thin filaments of galaxies weaving together into immense strands. Knots where filaments meet, called clusters and superclusters, and between them, enormous empty stretches called voids. Regions so vast that a beam of light would need hundreds of millions of years to cross them. The pattern looks eerily like foam on the surface of dark water, or like neurons in a brain, luminous. Threads and vast hollow spaces between. Astronomers had guessed at such a structure from earlier smaller surveys, and from computer simulations of how matter should behave under gravity. But Sloan's clarity changed speculation into something you could see with your own eyes. The cosmic web, as it came to be called, stretched in every direction, revealing that our own Milky Way rides one filament among countless others. Part of a local arrangement sometimes called the Laniakea supercluster, itself a swirl inside the greater flow. This was no simple scattering after an explosion. This was structure sculpted by physics across billions of years. Newer efforts built on Sloan's foundation. The Dark Energy Spectroscopic Instrument, DESI, began scanning the sky in 2021 from Kitt Peak National Observatory in Arizona, using 5,000 robotically positioned fibers to collect light from distant galaxies and quasars with breathtaking speed. Its goal is to map the expansion history of the universe by gathering data from more than 30 million galaxies and cosmic beacons. Each night it captures thousands of spectra, adding detail to the grand weave, sharpening our picture of how matter and dark energy have competed across time. When you look at these maps, sometimes shown in cross-sections that sweep out wedge shapes from Earth like slices of pie, you can feel the scale almost physically. Great tendrils of galaxies stretch across billions of light years, connected like river systems feeding into glowing seas. And between them lie black gulfs with almost nothing, voids so empty they make the distance between ordinary galaxies feel intimate. Yet even here the universe's expansion does not behave like a smooth, uniform tide. In regions where matter has gathered densely, clusters where thousands of galaxies huddle. Bound by dark matter's hidden gravity, the pull slows the local growth, fighting back against the outward drift. Inside voids, by contrast, there is little to resist the stretching. They expand faster, growing emptier and wider as time passes. Computer models now simulate this dance with great fidelity. Scientists feed into them the physics of gravity, dark matter, and dark energy. Then watch as tiny initial ripples like those COBE and WMAP first recorded swell into the vast spiderweb we see. The models show how, shortly after the Big Bang, slightly denser regions began to collapse under gravity, pulling in matter and slowing local expansion, while the emptier regions thinned and spread. Over billions of years, the pattern sharpened, filaments forming highways of galaxies, voids yawning into cold darkness. It is strange and humbling to imagine that what looks random on a starlit night is, when seen across cosmic distances, part of a coherent and beautiful structure. Every familiar galaxy, Andromeda, the Whirlpool, the Sombrero, is a single pearl on one of these glowing threads. Even our own solar system drifts quietly inside a small arm of the Milky Way, which itself flows along a filament drawn toward a gravitational center called the Great Attractor. Though what exactly creates that pull remains under study, standing at an observatory while such maps are discussed, you might feel a shiver that is not from cold mountain air, but from scale. The data flowing from Sloan and DESI arrives as streams of numbers. Redshift values, positions in right ascension and declination. Yet they add up to something almost living. A universe with architecture. Not designed, but shaped by the slow laws of physics acting over unimaginable time. It is a far cry from the simple mental picture of an expanding bubble. Instead, expansion and gravity have carved an intricate web, its threads rich with galaxies, and its hollows deepening as dark energy drives them apart. There is poetry in the idea that we live not in a featureless void but along a filament. Like tiny travelers on an intergalactic highway, with neighboring galaxies bound to us for now, but destined eventually to drift away as acceleration carries them beyond our reach. When you see the full map, often rendered in luminous blues and golds on black, you understand why astronomers speak of the cosmic web with reverence. It is not only a chart of where things are. It is a record of how everything came to be, the interplay of slight imperfections in the early plasma. Gravity's patient pull, and the restless push of dark energy shaping a masterpiece. These surveys continue every night, quietly feeding new coordinates into the great model. Each additional galaxy measured sharpens the weave, lets us test whether dark energy has stayed constant or shifted with time, and helps answer the larger mystery of the universe's fate. But beyond data and theory, there is something deeply human in these maps, a yearning to know. Not just what the universe looks like, but where we belong inside it. For now, the answer is a single faint thread among billions, drifting within a pattern so vast we can only glimpse its shape and wonder at the silent forces that built it. At the dawn of the 20th century, when the night sky still seemed like a fixed dome studded with distant lanterns, Albert Einstein quietly changed everything about how we think of space and time. Until then, most people, even scientists, imagined the universe as a grand stage, an empty, invisible room where stars and planets drifted like actors across a motionless floor. Isaac Newton's laws had worked well for centuries by assuming this rigid backdrop. Time ticked evenly everywhere. Space stretched without limit and without influence. And gravity was simply a force pulling one mass toward another across that void. Yet, there were cracks in this comfortable picture, small but growing, found in the behavior of light and the precise orbit of Mercury and the strange equations of electromagnetism. Einstein spent years wrestling with those cracks. And in 1915, he presented general relativity, a theory so radical that it replaced the stage with something alive. In this new view, space and time fused into a single entity, spacetime, and far from being empty and passive, could bend, stretch, and ripple. Massive objects such as the sun or a black hole do not tug on planets in the old Newtonian sense. Instead, they curve the fabric around them, and the planets follow the easiest paths through that curved geometry. Just as marbles roll along dips in a flexible sheet, time itself is part of this fabric. Clocks run a little slower near heavy masses, and light shifts to the red when it climbs out of deep gravitational wells. The effect is gentle here on Earth, but grows overwhelming near stars and black holes. This vision was hard to accept at first. It demanded letting go of centuries of mental habit, yet evidence soon followed. In 1919, during a total solar eclipse, Sir Arthur Eddington led an expedition to the island of Principe off the coast of Africa and to Sobral in Brazil to measure whether starlight passing near the sun was bent by its gravity. The results matched Einstein's predictions. Newspapers announced that Newton's universe had been overturned. Einstein, previously an obscure patent clerk turned theorist, became a global name overnight. The image of grids bending near stars, so common now in documentaries and textbooks, began to take hold because the math worked and the cosmos agreed. But Einstein himself, even as he gave us this flexible stage, was uneasy with what his own equations implied about the whole universe. When he first applied general relativity to cosmology in 1917, the math suggested that space could not remain static. It should either expand or contract under the weight of gravity. At the time, though, most astronomers believed the universe was steady and eternal. So Einstein inserted a new term into his equations, the cosmological constant. This constant acted like a repulsive pressure, balancing gravity so the cosmos could remain frozen and unchanging. For years this seemed reasonable then. In the 1920s, Esto Slipher and later Edwin Hubble showed that distant galaxies were not at rest at all. Their light was redshifted, fleeing in all directions. The universe was expanding. Einstein reportedly met Hubble at Mount Wilson and, after seeing the evidence, dropped his constant, calling it his biggest blunder. He felt he had forced nature into an assumption it did not need and missed the chance to predict cosmic expansion before the observations came. Ironically, the story did not end there. Decades later, in the late 1990s, the teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees used type Ia supernova to show that the expansion was not slowing but accelerating. Something like Einstein's constant, a uniform energy of empty space, seemed to exist after all. Cosmologists revived the symbol lambda lambda, recognizing that perhaps Einstein had been right to include it, though for reasons he never dreamed of. Today, when scientists speak of dark energy, the simplest explanation is still a cosmological constant. The idea that vacuum itself has a small but persistent energy density that drives galaxies apart ever faster, it is striking to picture. Einstein's own hesitation, his notebooks from those years show careful crossings out and revisions as he tried to fit his equations to the steady cosmos everyone expected. He could not have known how the data would eventually circle back and vindicate at least part of his impulse. The flexible stage he imagined has become the standard framework of modern physics, and the constant he regretted has returned as the most accepted, if mysterious, answer to why expansion accelerates. General relativity's picture of spacetime is not just an abstract construction. We see its fingerprints everywhere. GPS satellites adjust their clocks to account for time dilation. Gravitational lensing lets us map invisible dark matter when light from galaxies bends and arcs around clusters. The 2015 detection of gravitational waves by LIGO caught spacetime itself, ringing like a drum after black holes merged. These are direct measurements of a universe where space and time move, twist, and carry information. If you visualize it at night, standing beneath the Milky Way, imagine not a black void, but a silent, pliable ocean, responsive to every massive island floating within it. The sun pulls Earth not by reaching across emptiness, but by shaping the ground underfoot. A clock on a satellite ticks slightly differently than one on your wrist because it moves in a gentler gravitational curve. A beam of light bends minutely as it passes Jupiter, following the geometry carved by the planet's mass. This flexible stage also changes how we think of the universe's fate. Expansion itself is not a movement through static nothingness. It is the stretching of the fabric. When astronomers measure galaxies receding, they are watching this living grid grow. When they speak of dark energy and the cosmological constant, they mean the stage itself carries some deep property that pushes outward. It can feel strange and abstract, but the truth is deeply physical. The equations have been checked across a century. In laboratories with pulsars, with spacecraft at the edge of the solar system. Each confirmation deepens the idea that space and time are not a container, but a participant. Einstein once said his greatest joy came not from any single prediction, but from seeing nature obey the strange beauty of his theory. Even if he could not have guessed how the constant would return, the idea of a living cosmos, one with no fixed stage, where the rulers and clocks themselves yield to gravity and energy, is his enduring gift. And every night when we look upward and sense both vastness and motion, we are feeling what he tried to describe: the universe as an active, restless fabric, still stretching and curving in ways that continue to surprise us in the dark of space. 1,000,000 miles from Earth, a great machine unfolds itself like a flower made of gold. This is the James Webb Space Telescope. Launched on December 25, 2021, after decades of planning, argument, and engineering so delicate that a single tear in the thin golden mirrors could have ended the dream. It traveled not to low Earth orbit like Hubble, but out to the second Lagrange point, L2, a place of quiet gravitational balance beyond the reach of Earth's bright warmth and shadow. There, shielded by a tennis court-sized sunshield of silver fabric, it settled into cold so deep its instruments could detect heat no stronger than a candle on the moon seen from Earth. Its goal was as ambitious as anything. Humans have attempted to look back further than any eye has seen, into the earliest era after the Big Bang, when the first galaxies were assembling and the cosmic night was giving way to light. For most of the 20th century, even with Hubble's exquisite vision, the farthest we could see was a few 100 million years after the Big Bang. Those galaxies were small and faint, tiny clumps of stars just beginning to form. Cosmologists assumed the earliest ones should be dim, irregular, and chemically simple after all. There had been little time to forge heavy elements or build grand spirals. Webb was built in part to confirm this, to catch the faint red light stretched, almost beyond detection by the universe's expansion, and bring back baby pictures of young, chaotic galaxies. Its first deep field, released in July 2022, stunned even the teams who had built it. A patch of sky no bigger than a grain of sand held thousands of galaxies, some whose light left when the universe was less than 400 million years old. But stranger still, many looked surprisingly mature. Their stars seemed older than expected. Some already contained heavier elements, like oxygen and neon, a sign of multiple generations of star birth and death. Structures appeared too organized, disks and clumps where theory had said only formless clouds should exist. Astronomers found themselves both thrilled and unsettled. The standard model of cosmology, it's built on general relativity and refined by decades of microwave background mapping and large-scale surveys, had painted a clear timeline after the Big Bang. There was an age of darkness when hydrogen and helium floated unlit. Then the first stars ignited around 200 to 400 million years and slowly merging into primitive galaxies. But Webb's infrared eyes, so sensitive they could catch single photons traveling for over 13 billion years, saw hints that complexity arrived faster than expected. It was not that the entire expansion theory failed. Redshift still matched the stretching of space. But details about how quickly matter cooled and clumped seemed incomplete. Some researchers whispered about cosmic dawn being busier than our models allowed. Papers appeared almost weekly in the months after those first images, proposing explanations. Perhaps early stars were far more efficient at producing heavy elements. Perhaps black holes formed and grew faster, shaping galaxies with jets and gravity. Perhaps dark matter behaves in slightly different ways than the simplest cold dark matter picture assumes. A few even speculated cautiously whether our understanding of expansion itself might need subtle correction, not abandonment, but refinement. Yet part of the wonder lay in how science responds. These surprises did not break the idea of an expanding universe. They sharpened it. Webb's instruments, particularly its near-infrared camera, ANRCam, and near-infrared spectrograph, ANRESPEC, delivered redshifts that confirmed distances and times. Expansion remains real and measurable. The puzzle is how quickly structure grew within it. That difference matters because it touches the invisible scaffolding of the cosmos, dark matter, star formation, feedback from early black holes, When your telescope begins to show massive, complex galaxies only a few 100 million years after time began, it forces a deeper look at the first chapters of cosmic history. You can picture the scientists confronting this in real time. Images arriving on screens at the Space Telescope Science Institute in Baltimore. Raw infrared light turned into faint points and swirls. Some of those points carry names like GLASSC13, a galaxy candidate possibly existing just 300 million years after the Big Bang. It's older and brighter than it should be. Spectra reveals starlight surprisingly rich in heavier atoms, suggesting entire cycles of birth and death already happened in cosmic youth. The excitement is palpable. Long nights are spent cross-checking data, making sure these are not misinterpretations of dust or contamination. The instruments hold steady. The findings remain. There is something profoundly human about how this unfolds. We build a tool of extraordinary delicacy, launch it across 1,000,000 miles of empty dark, aim it at a spot of sky no one would bother to glance at, and it returns a view that quietly rewrites what we thought we knew. The theory of expansion, anchored since Hubble and Einstein and strengthened by COBE, Womack and Planck, still holds its ground. But Webb has opened a door into a time when that expansion was young and wild, revealing a richness and speed to the birth of galaxies that textbooks had only guessed. The story is still being written. Each new deep field, each faint arc lensed by intervening clusters, each spectral fingerprint of ancient starlight adds to the timeline. In a few years, with data from DESI and other surveys combined with Webb's gaze, cosmologists may update the models of how matter cooled, how the first halos collapsed, how black holes seeded structure. Perhaps some quiet parameter in our equations will shift. Perhaps we will need a new term as profound as Einstein's once maligned constant. Whatever the outcome, the journey shows that the universe can still surprise us. And that expansion is not a solved riddle, but a living investigation. Standing beneath the night sky, knowing this changes how one feels about those faint lights. They are not just ancient. They may be older and more intricate than we imagined, survivors of a turbulent dawn when time itself was barely awake. And somewhere beyond our seeing, more of them wait, their light already on its way, carrying news from the first flicker of order out of fire. The James Webb Space Telescope, with its gold mirrors shining cold and perfect, is not just peering back. It is reminding us that every answer births another question, and that even the vast, expanding universe can still surprise those who dare to look deeply enough. Not long after the idea of an expanding universe took root, another, more unsettling question appeared. If the cosmos had truly begun in an unimaginably dense and hot state, and then swelled outward for billions of years, why does the sky look so remarkably even in every direction? When the first detailed maps of the cosmic microwave background emerged in the late 20th century, scientists saw a young universe astonishingly uniform, the same temperature, the same density to 1 part in 100,000, across regions that were so far apart that light could never have crossed between them in the time since the Big Bang. This puzzle, it's called the horizon problem, was simple to state but impossible to ignore. How could distant parts of the universe be so alike if they had never shared information or heat? Another problem lurked alongside it, the flatness problem. Einstein's general relativity allows many possible shapes for the cosmos. It could be curved like a sphere, saddle-shaped, or perfectly flat so that parallel lines never meet. Yet measurements, even with early instruments, suggested an extraordinary balance. The density of the universe sat precisely on the knife edge required for flatness. If it had been slightly higher, gravity would have made the whole thing collapse long ago. Slightly lower, and it would have flown apart too fast for stars to form. The fine-tuning seemed improbable, like balancing a pencil on its point, in the late 1970s and early 1980s. A young American physicist named Alan Guth wrestled with these riddles. Guth, working at SLAC and later MIT, had been studying the behavior of fields thought to have existed in the very early universe. Strange energy forms predicted by particle physics. In December 1979, while leafing through old notes late at night, he realized something striking. Certain high-energy states could cause space itself to expand at a staggering, almost incomprehensible rate. He scribbled in his notebook "spectacular realization" and circled it. Because if such an expansion occurred just after the Big Bang, it could stretch and smooth everything so quickly that the horizon and flatness puzzles would vanish. The idea he presented in 1981 became known as cosmic inflation. According to this theory, in the first tiny fraction of a second, far less than a blink, around 10 to 36 seconds after the Big Bang, the universe underwent a burst of exponential growth. Regions that had once been in close contact were blown apart faster than light could chase their parting edges. But because they began close enough to share the same conditions, they retained a near-perfect uniformity. Tiny quantum fluctuations, random jitters in the primordial energy field, were stretched to, becoming the seeds for the ripples we now see in the microwave background, and that would later grow into galaxies. Inflation was radical but elegant. It solved the horizon problem by explaining how distant parts of the sky could once have touched. It solved the flatness problem by stretching any initial curvature to near zero. Just as a balloon inflates so much that a small patch seems flat. It even explained why we don't see exotic relics like magnetic monopoles that some early theories predicted inflation would have diluted them beyond detection. At first, the proposal was met with curiosity and skepticism. It was bold to suggest an event so violent and brief happening before anything we could hope to observe directly. But as the 1980s and 1990s rolled on, evidence began to align. The COBE satellite's 1992 detection of tiny temperature ripples in the cosmic microwave background looked just like the kind of stretched quantum fluctuations inflation would leave behind. Later, WMAP and Planck refined these patterns, showing the statistical fingerprints predicted by inflation, slight differences in temperature, distributed in a way that matched an exponentially expanded, nearly flat universe. Picture it visually, though no human eye could have seen it. In a time so early it defies comprehension, the entire observable cosmos. Everything we now call galaxies and stars and people was once a speck smaller than an atom. Then, driven by a high-energy vacuum-like field, sometimes called the inflaton, it swelled at breathtaking speed, doubling in size again and again, perhaps 100 times in far less than the time it takes light to cross a single proton. In an instant, it became vast, smooth, and poised for the slower, gentler expansion we trace today. Alan Guth's breakthrough inspired others, Andrei Lind, Alexei Starobinsky, and many more to refine the details. Models of new inflation and chaotic inflation explored how the energy could end, allowing the universe to cool and ordinary matter to form. Experiments on Earth could not reproduce such conditions, but the sky itself became the laboratory. Each new generation of cosmic background mapping tested inflation's predictions with increasing precision. And so far, the theory has stood firm, though no one knows exactly what field or particle powered it. There is humility in this story. A sleepless physicist paging through calculations found a way to answer some of the deepest puzzles about existence. And though the mechanism is still mysterious, the imprint of that ancient growth spurt remains in the heavens. When we look at the modeled sky maps from Planck or WMAP, we are staring at the stretched-out echo of quantum randomness, right across trillions of light years. Inflation also deepened the question of what the universe expands into. It suggested our visible cosmos might be just one bubble among many, each born from its own inflationary burst, a multiverse swelling beyond any horizon we can reach. That idea remains speculative, but it flows naturally from the math. If space can expand so violently once, perhaps it still does elsewhere, spawning other realms forever outside our contact. Yet even without that leap, inflation gave modern cosmology its spine. It took a young universe that seemed improbably neat and made it understandable, not by magic but by a single, breathtaking event at the edge of time. The sudden breath smoothed the chaos, set the stage for galaxies, and left behind the faint unevenness that would grow into every structure we see. And while we may never witness that first instant, every new deep field image, every faint pattern in ancient light, is a whisper from it, a reminder that our entire sky was once smaller than a dot, and then, in an unimaginable flash, became a place wide enough to hold everything we know. When we speak of the universe, it is easy to imagine that what we can see is all there is, as though the great dark sky were a full map, its edges marked by the faintest stars our instruments can detect. Yet the truth is far stranger and far lonelier. The part of the cosmos available to us is only a small bubble carved out by light's patient journey since the beginning of time. A sphere of reach determined not by walls, but by the simple fact that nothing can outrun light. The Big Bang happened about 13.8 billion years ago. But because space itself has stretched as that light traveled, the region we can observe now has a radius of about 46 billion light-years. Beyond that shell, more universe almost certainly exists, perhaps infinite, perhaps curving back on itself. But whatever lies there is cut off by time and expansion. This observable horizon is not static. Each second that passes, light from slightly farther away reaches us. Our bubble grows, but so too does the space between everything. It is a race we are slowly losing. In the 1990s, when the faint glow of distant Type Ia supernova revealed the accelerating expansion of the cosmos, a new and sobering realization emerged. Not only is there a visible limit shaped by the age of the universe, there is also a deeper event horizon beyond which galaxies, though they exist right now, will drift away faster than their light can ever reach us. Even if we wait forever, their final rays already on the way will arrive, and then nothing new from them will follow. They will fade beyond contact, unreachable forever. This idea that we inhabit a temporary island of connection is one of the most unsettling gifts of modern cosmology. It means our cosmic neighborhood is shrinking in a profound sense, even while space itself grows. Galaxies close enough now to be seen will, over billions of years, slip past an invisible boundary. Future observers, if any remain, will see less and less. First, the faint smudges of distant spirals thinning out. Then the nearest clusters fading, until eventually only the stars of our own local group, gravitationally bound and refusing to be swept away, remain. All else will vanish into cold darkness beyond reach. You can imagine this visually by picturing a dark ocean under starlight. Our telescopes are small lanterns catching ships on far horizons. Those ships are moving not because they choose to, but because the water between us stretches. Some sail so fast that, though their beacons shine now, the sea expands quicker than their light can close the gap. There is no wave we can send, no engine we can build to chase them. The very medium of travel grows too fast. They slip behind a horizon not of distance, but of speed. When Edwin Hubble first plotted the expansion in 1929, he could not have foreseen this future isolation. His discovery that galaxies recede set the stage. But the acceleration revealed by Saul Perlmutter, Brian Schmidt, and Adam Rees 70 years later turned the universe from a gently coasting sea into a runaway tide. Now cosmologists calculate that any galaxy more than about 16 or 18 billion light-years away today is already lost to us. Its light, no matter how long we wait, will never arrive. The cosmic event horizon, like the one around a black hole, is not a physical barrier, but a limit of causality beyond it. Events can no longer influence our world, even our current horizon. The so-called particle horizon marking how far light has traveled since the Big Bang is deceptive. We say we can see 46 billion light-years, but that is because the space itself expanded while the light was en route. When those first photons left, the regions they came from were much closer. The image we have is not of a fixed edge, but of a living, changing boundary shaped by time's passage and space's restlessness. For astronomers, this horizon is both a challenge and a source of awe. Instruments like the James Webb Space Telescope push vision ever nearer to the edge, gathering light from galaxies less than 400 million years after creation. Each such detection is like a faint postcard from a place we can never visit. Even if we imagined starships of impossible speed, the simple expansion of space forbids the journey. The distance grows faster than any vessel could fly. The concept forces a change in perspective. The universe is not a single whole we can one day map completely. It is, for each observer, a personal bubble of knowable reality. It's defined by how long light has had to travel and by the restless growth of the fabric it crosses. Another civilization elsewhere would inhabit its own bubble, overlapping ours partially, but not entirely. There is no absolute shared edge, only a horizon tied to each vantage point. This horizon is also a time machine of sorts. When we look at a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. Its current state is forever beyond us if it has since crossed the event horizon. The image is ghost-like, light still coming from a world that now drifts into unreachable dark. And yet there is a deep, quiet beauty in knowing this. The night sky is not only a record of where things are, but of what once touched us and then receded. It is a message from the past of the universe, carried as far as physics allows. That we can know about this limit and describe it with precision using general relativity, redshift surveys, and the maps made by COBE, WMAP, Planck, and DESI is itself extraordinary, standing outside under clear stars. One can almost feel the boundary, though it is invisible. Some lights reaching your eyes tonight began their trip when Earth was molten, others when life was still single-celled, others before galaxies like ours fully formed. And beyond them are lights that will never arrive, paths already diverged. The universe is generous, but not infinite in what it lets us see. Our bubble will continue to grow for a while. New ancient photons are still on their way, bearing stories from slightly farther. But the acceleration of expansion ensures that the frontier will also slip away faster than we can chase it. To live in such a place is both limiting and astonishing. We are bounded by light and time, but within that boundary we have learned to read the messages of everything we can reach. Beyond lies silence we can measure but never cross, a fading horizon where the last signals slide away into night. When we try to imagine the shape of the universe, our minds reach for simple pictures, a giant ball, a flat sheet, perhaps even a bowl bending inward. But the reality is stranger and more abstract than anything our senses have prepared us for. Geometry on cosmic scales does not behave like the geometry of tabletops and playgrounds. It follows the rules of general relativity, where space itself can be curved by energy and mass, and where lines we assume should stay parallel might converge or diverge across unimaginable distances. For much of the 20th century, cosmologists wrestled with three broad possibilities: that the universe is flat and infinite, that it is closed like the surface of a sphere, but in 3 dimensions, or that it is open and saddle-shaped, curving negatively so parallel paths drift apart forever. Each picture brings its own strange implications. A flat cosmos means that if you could build an impossibly long ruler and march along it, you would never curve back to where you started. Space would go on without end and without edges. A closed universe would be finite yet unbounded. Like the surface of the Earth but extended into an extra dimension we cannot picture. Travel far enough, and you could, in theory, return to your starting point, though the journey would exceed the lifetime of stars. An open, negatively curved universe would be even more alien. Lines that begin side by side would drift apart, and triangles would have angles adding to less than 180 degrees. Each model shapes not only distance and travel, but the fate of everything. Whether expansion might one day stop or continue without limit, for decades. Astronomers searched for a way to measure the cosmic curvature directly. One key came from the afterglow of the Big Bang itself. The cosmic microwave background mapped first, roughly by COBE in 1992, and later with stunning precision by WMAP in 2003 and Planck in 2013. Those ancient photons carry an imprint of sound waves, pressure ripples, moving through the hot plasma of the early universe, known as baryon acoustic oscillations. These ripples froze into place when atoms first formed and light could finally travel freely. About 380,000 years after the Big Bang, the scale of those ripples provides a kind of standard ruler, a known size imprinted across the sky, by comparing how large those ripples appear in the microwave background. And in the clustering of galaxies today, Cosmologists can test the curvature of space. If the universe were closed and positively curved, the ripples would look slightly larger because space would bend inward, magnifying them like a fisheye lens. If open, they would look smaller. Measurements by Planck and by large galaxy surveys such as the Sloan Digital Sky survey and its successors have found the scale almost exactly as expected for a flat geometry. Within the margin of error, the cosmos appears to be very nearly flat, so flat that its radius of curvature, if any, would be far beyond the observable horizon. There is something at once comforting and disturbing about this. Flatness means the familiar Euclidean rules we learned in school hold on grand scales. Parallel lines stay parallel. Triangles behave normally, and there may be no ultimate wraparound or edge. Yet it also means the universe could be infinite, stretching without center or boundary in all directions. Infinite space is unsettling because it denies any privileged place. There is no middle, no favored vantage point, not even a cosmic outside to define an inside. Every observer, no matter where, sees galaxies fleeing just the same. Because the expansion is uniform, even if the universe is only very nearly flat and actually closed on scales larger than we can see, it would still feel infinite to any inhabitant. The curvature would be so gentle that no journey, no observation could reveal it. Cosmologists speak of this with a quiet humility. The best data we have from Planck's temperature maps to surveys like DESI that track baryon acoustic oscillations and galaxy distributions says we live in a cosmos with curvature so close to zero we cannot measure the difference. But close to zero leaves room for deep possibilities. Just beyond our view, the idea of a centerless infinite universe took time to settle in the human imagination. When Copernicus displaced Earth from the center of the solar system, it was shocking, but still left the sun as an anchor. Later we learned our sun is just one star among hundreds of billions in the Milky Way. And then Edwin Hubble showed the Milky Way as one galaxy among countless others. Now even the notion of a cosmic center has vanished. Expansion happens everywhere at once, and every observer can think of themselves as stationary while space grows between all things. There is no privileged spot where the Big Bang happened. It happened everywhere, because it was the creation of space itself. You can try to picture this under the night sky, though it is hard. Imagine walking across a featureless plain that never ends. No edge, no curvature your eyes can detect. Or imagine sailing on an ocean so vast that its horizon is always just beyond reach, with no island to mark the center. The Milky Way arches overhead not as a central spine, but as one thread among billions in the cosmic web. And beyond it, space continues, not necessarily with more galaxies exactly like ours forever, but with no boundary we could ever find for scientists. This near flatness is also a clue about the universe's early moments. Inflation, that sudden breath proposed by Alan Guth and others, would have stretched any initial curvature smooth, just as a small patch of balloon looks flat when inflated enough. The measurements we make today are in part a vindication of that idea. The slight ripples we detect, the tiny anisotropies in the microwave background, are consistent with quantum fluctuations blown vast by inflation in a nearly flat cosmos. Yet beyond the technical satisfaction there remains the human response, a mixture of wonder and vertigo. We inhabit a universe that seems to have no edge, no preferred place, and perhaps no end. Our maps, so impressive with their filaments and voids, cover only a sphere of visibility floating in something we cannot fully chart. The comfort comes from knowing the rules seem coherent. The unease comes from realizing how small and unanchored we are within them. Flatness does not mean simplicity. It means boundlessness, a stage so wide that even our most powerful telescopes are just tiny. Lanterns thrown into a night without shore. When scientists talk about the observable universe, they mean the sphere of space from which light has had time to reach us since the Big Bang. A fragile bubble about 46 billion light-years in every direction. But general relativity does not say this bubble is the whole story. It only marks the edge of what we can see. Beyond it, there may be more of the same, or something stranger altogether. Once the idea of inflation took hold in the early 1980s, The notion that the universe underwent a breathtaking burst of expansion in its first instance, some theorists noticed that the math did not require inflation to stop everywhere at once. Instead, it could continue endlessly in remote regions, spawning countless pocket universes, each its own bubble of spacetime with its own laws of physics. This concept, called eternal inflation, grew naturally out of Alan Guth's original insight and was sharpened by thinkers like Andre Lind, Alexander Vilenkin, and Paul Steinhardt in the years that followed. In this picture, our entire observable cosmos is just one bubble in a vast froth, a single, inflating patch that cooled enough to form stars, galaxies, and life, while elsewhere inflation still rages, or has ended in different ways. Each bubble could have different fundamental constants, different particle types, perhaps even different numbers of spatial dimensions. Some might be sterile and empty. Others might teem with strange forms of matter and energy. The multiverse, as this grand possibility came to be called, is not an attempt to escape data, but an implication of how quantum fields behave under inflation. Energy can decay at different rates in different places, creating a patchwork quilt of universes beyond all horizons. Yet a theory so grand cries out for evidence. If other bubbles exist, could they ever touch or leave a mark? Some cosmologists began searching for what they poetically call bruises subtle, scars in the cosmic microwave background that might record ancient collisions between our bubble and another, before inflation pushed them apart. The idea is simple but haunting. If two universes once bumped during their rapid growth, the impact might have sent shock waves into the hot plasma that later became the microwave background, leaving circular patterns or temperature anomalies imprinted across the sky. Satellites like Luma Pay and Planck have been scoured for such signs. Planck's maps of the microwave background are so precise that they reveal tiny variations at the level of microkelvins across the sky. Teams have searched for suspicious concentric rings or unusually cold or hot spots. One region called the cold spot, a patch of sky in the constellation Eridanus, sparked years of debate. Some wondered if it might be evidence of a bubble collision. Others argued it was simply a statistical fluke or the shadow of a vast void of galaxies in that direction. To date, no clear, unambiguous bruise has been found, though the hunt continues. The absence of obvious scars does not disprove the multiverse. Collisions could be rare or leave subtler traces than we can currently detect. Other approaches probe indirectly. Particle physicists study inflation models in the hope of learning whether eternal inflation is generic or rare. Observatories like Barr at the South Pole and experiments chasing the faint polarization of the cosmic microwave background look for gravitational waves from the first instant of time, ripples that could confirm or constrain inflation's wildest versions. Even so, the multiverse sits at the edge of science, not fantasy, but a hypothesis testing the limits of what data can reach. To visualize it, imagine dropping stones in a vast dark pond. Each stone splash creates a spreading ring. If two rings intersect, ripples distort and overlap. Our bubble might once have brushed against another's ring during inflation. Its scars still stretched across the sky we now map. Or imagine an endless field of soap bubbles forming and swelling. Each is a cosmos, some touching, some drifting alone. Their interiors forever cut off from one another once they pull apart faster than light can travel. Inside our bubble, the cosmic microwave background is the wall of light we see. But just beyond, more bubbles could drift unreachable. Unknowable directly, but implied by the same physics that gave us expansion, there is a philosophical weight to this possibility. Copernicus dethroned Earth from the center. Hubble stripped the Milky Way of uniqueness. Now inflation suggests even our entire universe may be one of countless siblings. Some find this thrilling, a deepening of humility. Others resist, arguing that science must remain tied to testable predictions. Still, the idea refuses to fade because it fits naturally with quantum theory and with what we know about how inflation works, for those who work with the data every day. The search is both technical and quietly emotional. In small offices, In remote telescope outposts, scientists comb through maps for faint overlapping ripples, asking whether a scar no wider than a few degrees on the sky could be a handshake from another reality. Each negative result sharpens the instruments and theories, but the question persists, even if no bruise appears. The mathematics behind inflation strongly hints that our bubble is not alone, standing under a night sky filled with stars. It is nearly impossible to feel this fully. Yet think of it, all the galaxies we have ever seen, all the cosmic web mapped by Sloan and Desi, every speck of matter and light we know. This might be a local event inside an endless and restless creation. There may be no final horizon, only the edge of what our light can reach before it gives way to others we will never touch. The thought is dizzying, but also strangely liberating. The universe we inhabit is already immense beyond comprehension. Beyond it there could be still more, each with its own dawn, its own fate, its own possibilities. No one can yet say whether the scars of other worlds are hidden in our sky, or whether inflation's mathematics will be replaced by something deeper. But the act of looking, of daring to ask what lies beyond our bubble, stretches imagination just as space itself stretches. The maps we have are not ends, but invitations, telling us that even in a cosmos we call home, there may be neighbors we can never visit, and realities forever beyond our reach. Pressing gently against the edges of our understanding, the path that led to our present. Picture of the universe was never smooth or inevitable. It was stitched together by countless ordinary hands and minds, each person reaching for some faint pattern in data that often seemed confusing or incomplete. And much of what we now accept came close to being overlooked or dismissed. The story of cosmic discovery is as fragile as the paper on which early astronomers penciled their notes. And at every step there were wrong turns, heated arguments, and results so faint they might have vanished if a single observer had lost faith. At the start of the 20th century, the universe was still thought to be just the Milky Way. Spiral nebulae appeared on photographic plates as smudged whirlpools, but most experts assumed they were small clouds inside our own galaxy. Yet even then, in the crowded offices of Harvard College Observatory, a woman working mostly alone was building a tool that would later crack the question of distance wide open. Henrietta Swan Leavitt, deaf and quiet but meticulous, studied variable stars called Cepheids in the Magellanic Clouds. Over years of patient work, she discovered that the period of a Cephid's brightening and dimming was directly linked to its true luminosity. The longer the period, the brighter the star really was. She published this quietly in 1912. In a small paper without fanfare, and at first the importance was not widely recognized. Her relation would later become the very yardstick Edwin Hubble used to measure the distances to Andromeda and beyond, proving the universe extended far past the Milky Way. Yet Leavitt herself died before Hubble's revolution, and her name barely made it into the headlines that followed, even after Hubble's 1929's discovery. That galaxies are fleeing from one another, the interpretation was debated. Some clung to static models. Others proposed tired light, a fading of photons rather than true expansion. Einstein himself had added and then retracted the cosmological constant, uncertain what the data demanded. The Big Bang was first used as a derisive phrase by Fred Hoyle, champion of a steady-state universe. On a BBC radio broadcast in 1949, for decades the debate between steady-state and expanding cosmos was fierce. Papers volleyed back and forth, observations challenged and dismissed. Only the accidental discovery of the cosmic microwave background by Arno, Penzias, and Robert Wilson in 1964, a hiss in a Bell Labs antenna no one could scrub away, finally tilted the argument decisively. Even then, theorists who had predicted that glow were on the verge of launching their own experiment when the engineer's report reached them. A twist of timing decided who would get credit for proving the hot beginning. Later, astronomers tried to weigh galaxies and clusters. Their numbers refused to add up. Stars alone could not explain the speed with which galaxies spun. Their outer edges moved too fast to be held by visible matter. In the 1970s, Vera Rubin and her collaborator Kent Ford spent long nights on mountain observatories, patiently measuring the rotation curves of galaxies. Rubin, one of the few women in her field at the time, often faced skepticism and dismissal. But her careful data showed again and again that galaxies are embedded in massive, visible halos, the first clear evidence of what we now call dark matter. At first, many resisted, looking for other explanations. And Rubin herself presented the results with calm persistence, knowing the weight of proof would have to overcome habit and prejudice. Today, dark matter is a central pillar of cosmology. But in those early years, the idea could have been shelved. Delayed for decades had the wrong voices prevailed. Even in the satellite age, accidents and fragile circumstances shaped progress. Cobb's mission to map the cosmic microwave background nearly lost funding more than once. Its instruments had to be rebuilt and cooled with elaborate cryogenics that engineers doubted would survive launch. Yet in 1992, its data revealed the tiny ripples that inflation had predicted. Temperature differences so subtle that without extraordinary care they might have been drowned by noise. WMAP and Planck, later missions that sharpened the view, relied on those first breakthroughs and on countless technical notes passed between teams. Handwritten formulas and calibration curves no one outside a small circle would ever read. Each discovery came not from a single stroke of genius, but from long endurance. Think of the notebooks, Leavitt's lined with dots and tiny brightness marks. Hubble's yellowing pages of distance and velocity. Rubin's careful graphs where speed refuses to drop with distance as Newton might expect. These records were often doubted, their makers asked to check again to prove beyond any personal bias. And they did, returning to the telescope. Correcting instruments, defending small signals against the tide of assumption. It is easy now to tell the story as if it was a smooth arc. We found Cephids. We measured galaxies. We heard the Big Bang's echo. We mapped the cosmic web. But in truth, there were long stretches when the next step seemed uncertain or impossible. Data were lost or ignored. Wars interrupted research. Funding vanished. Promising students left the field under pressure. The chain could have broken in many places. That it did not is as much about stubbornness and curiosity as about theory. There is something deeply human about this history. Our view of the universe infinite or nearly flat, expanding and seeded with dark matter. Driven by dark energy was built not by inevitability, but by fragile persistence. It depended on people willing to spend decades staring at faint signals. People whose work was sometimes undervalued or forgotten. People who corrected themselves and one another again and again until the pattern held. The cosmos as we know it is also a human artifact. A collage of careful eyes refusing to let silence and uncertainty win. Under a clear night sky, it can be moving to think of them. Leavitt's quiet diligence in Cambridge. Rubin's cold nights at Kitt Peak. Penzias and Wilson crouched in a white horn antenna cleaning away pigeons. Guth scribbling spectacular realization in a margin. Countless graduate students checking cables and counting photons. The vastness we describe so confidently today rests on the most delicate thread of patient observation. One misstep, one forgotten note, and the story might have taken decades longer to unfold. And so when we look up, marveling at an expanding universe, it is worth remembering how improbable it was that our small, fallible eyes learned to see it at all. When the notion of an expanding universe first reached beyond observatory walls, it did not stay a quiet technical idea. It slipped into books, poems, paintings, and speeches. Unsettling and inspiring minds far from the mountain domes where redshift was first traced. The image of a cosmos with no fixed edges and a beginning in time is a way of unsettling every story humans have told about place and permanence. Artists and writers seized on it quickly. In the 1930s and 1940s, just as Edwin Hubble's work began to circulate more widely, magazines published illustrations of spiraling galaxies racing away into infinite night. Poets wrote of light stretched thin with age, of stars fleeing like memories. Philosophers, long used to a static sky as a metaphor for stability, suddenly confronted a world where even the firmament was restless. After the Second World War, as physics matured and the Big Bang Theory edged past its rivals, expansion also took on symbolic weight. A universe with a birthday seemed to echo creation myths, yet without the certainty of divine blueprint. Some thinkers found hope in that, others deep unease. Jean-Paul Sartre and Albert Camus, though not cosmologists, wrestled with the loneliness implied by an ever-growing centerless cosmos. Later, Carl Sagan would turn the same idea to wonder, speaking of star stuff and ancient light to audiences on television in the 1980s, his voice carrying the expansion narrative into living rooms around the world. Yet the influence reached more concrete realms as well. In the tense decades of the Cold War, the race to understand space was not just about rockets and flags, but about knowledge itself. The Soviet Union and the United States poured money into astronomy and satellite engineering because space had become a new frontier of power. This competition, though born of fear and rivalry, pushed cosmology forward in practical ways. Instruments once meant for military or communication purposes found second lives in cosmic investigation. The giant horn antenna at Holmdel, where Penzias and Wilson heard the microwave background, had been built to track early satellite relays. The precision demanded by intercontinental ballistic missile systems forced improvements in guidance and detection that later helped telescopes aim and measure with exquisite accuracy. Sputnik's beep in 1957 and Yuri Gagarin's flight in 1961 jolted the United States into creating NASA and funding research not just for manned missions but for understanding the space those missions entered. When the Apollo program landed humans on the moon in 1969, it was a triumph of engineering and politics. But it also left a legacy of instruments and experience that fed directly into space science. Rocketry developed to lift warheads delivered satellites like COBE, WMAP, and eventually Planck, each one mapping the expanding cosmos with precision unimaginable to Hubble's generation. The same Cold War budgets that built bombers also built cryogenic coolers and gyroscopic stabilizers that would one day stare at ancient light. Headlines through these decades, often mixed. Wall with fear, images of rockets lifting through Florida sky, countdown clocks at Cape Canaveral. Speeches about the final frontier. Behind that noise. In quiet offices at NASA's Goddard Space Flight Center or the European Space Agency, scientists turned those tools toward deeper questions. As radio telescopes improved to watch Soviet satellites, they also became sensitive enough to catch whispers from quasars and pulsars. Testing relativity and refining cosmic distances, the global network of tracking stations built to follow spacecraft later served to receive faint signals from deep space probes that in turn measured the interplanetary, medium, and cosmic microwave glow. Meanwhile, expansion seeped into culture in ways less technical, but no less real. Painters borrowed its imagery, great arcs and receding galaxies, to convey loneliness or transcendence. Science fiction writers, from Arthur C. Clarke to Ursula K. Le Guin, wove stories around endless outward drift, worlds cut off by light years in accelerating space. Even political language borrowed from cosmology. Presidents spoke of new frontiers, and the term Big Bang migrated into headlines about economics and technology. The universe's restless growth became a metaphor for human ambition and risk. Philosophy and theology also adapted. Some thinkers embraced the Big Bang as a moment akin to creation, a time when all laws and matter were once compressed to a single seed. Others saw in expansion a deep existential message that change and impermanence are woven into the very fabric of existence. Not just human life, but the cosmos itself. The Catholic priest and physicist Georges Lemaître, who first proposed what would become the Big Bang model, wrote with quiet reverence about a primeval atom, blending his scientific insight with spiritual awe. Decades later, Stephen Hawking would speak of a universe with no boundary, still expanding, but potentially self-contained, needing no outside cause. These conversations spilled into universities and coffee houses alike, reshaping how ordinary people talked about origins and endings. There was a feedback loop between science and imagination. The vast sums and grand projects of the space race built instruments and images that then entered popular consciousness. Photographs of Earth as a pale blue marble against black space, taken by Apollo astronauts, fed a sense of fragility and unity that filtered into environmental politics and global thinking. At the same time, The idea of boundless expansion fueled both optimism and dread about humanity's future. The sense that if space itself could grow without end, so could exploration and knowledge, but also that we are small, brief, and perhaps cosmically alone by the late 20th century. When Cobe revealed the faint ripples of the early universe and WMAP sharpened the map, the public was ready to listen. Television specials, planetarium shows, and best-selling books carried words like dark energy, inflation, and accelerating cosmos, far beyond laboratories. Yet behind every headline and glossy image, there remained quiet rooms of researchers running calibration tests, arguing over error bars and poring over faint plots of temperature differences. The grand story, from Cold War rockets to living room documentaries, depends on that quiet calculation. If you stand today before one of the surviving rockets at Cape Kennedy or gaze at a Planck all-sky map in a museum, you can feel the crossing of two worlds, the noise of politics and competition and the slow, patient science that took those tools and turned them toward the oldest light. Expansion, once a fragile, contested idea, now informs art, shapes the language of ambition, and even echoes in diplomacy and culture. Yet at its core, it remains a simple, startling discovery that the stage itself moves carried from mountain observatories to superpower. Boardrooms and back again. Proof that human curiosity can survive and even thrive amid fear and rivalry, and still find room to wonder far ahead of us. So far that no calendar can carry the numbers comfortably. The universe becomes a very different place than the vibrant, web-filled cosmos our telescopes now reveal. Expansion, which we measure with such care today, will keep going and going, tugged ever faster by dark energy's persistent push. Galaxies not bound to our own small neighborhood will continue to drift away until their light can no longer outpace the stretching of space. Each decade and century sees the sky subtly thinner, but the true change unfolds across timescales that humble imagination. In perhaps 100 billion years, long after every recognizable constellation has warped beyond recognition, observers in what remains of the Milky Way and its local companions will look up and see no great cosmic web, no chains of distant clusters, only a cold, black gulf beyond a few lonely islands of stars. Astrophysicists call this future cosmic isolation Andromeda, the Triangulum Galaxy. And a scattering of dwarf galaxies is bound tightly enough by gravity to resist the general expansion, so it will remain together while everything else slips away. Over tens of billions of years, these galaxies will merge into one enormous elliptical, sometimes dubbed Milkomeda, a swollen star city, adrift in silent dark. For any civilization alive then, the night sky will be strangely claustrophobic. They will have no easy evidence of an expanding universe. Every other beacon that once revealed cosmic history will be gone beyond the event horizon. The faint afterglow of the Big Bang, our cosmic microwave background, will have cooled and stretched so far it will be undetectable. If scientists exist then, they will find themselves in a small, dark bubble, with almost no hint that there was once a larger story. Time does not stop there. It crawls onward in a way almost beyond language. Stars like our sun will long since have burned out, replaced by faint red dwarfs glowing dimly for trillions of years. These smallest stars, the universe's patient embers, can last up to 10 trillion years, feeding slowly on hydrogen with an efficiency our sun could never match. But even they will eventually fade, leaving only white dwarfs cooling in the dark. Over unimaginable stretches, those remnants will cool to black, their heat leaking away until they are as cold as the background around them. Meanwhile, cosmic expansion continues to stretch space itself. The night sky of that deep future will have no grand arcs of the Milky Way, because it will have long since merged into Milkomeda's diffuse glow. No nearby galaxies will decorate the horizon. The black will be near total, broken only by whatever local stars still shine. For creatures born into such a time, the idea of a vast dynamic universe might seem fantasy. Their telescopes, however perfect, would find nothing beyond their home cluster. Expansion would have erased its own evidence. On still longer scales, the darkness deepens, Planets will drift or spiral into their dead suns. Stellar remnants may collide or evaporate. Even the black holes left behind by collapsed giants will slowly lose mass, evaporating through Hawking radiation over numbers of years so great they must be written as powers of 10. Each one goes out, not with a flash, but with a long, quiet fade, until the universe is nearly empty of structure. This imagined future is called heat death. Not a fiery end, but the final leveling of temperature and energy. Everything spread thin, and even so there's no more work to be done. No more clumping of matter to fuel stars or life. To think about such epochs is dizzying, because our own history feels microscopic against them. Humanity has existed for a few 100,000 years. Civilization for 10,000. Our telescopes for mere decades. Yet the universe has plans stretching across trillions of years, eras when everything we know, galaxies, stars, even atoms in some forecasts may become irrelevant against the smooth, cold sea of spacetime. The loneliness implied by such a future can seem unbearable at first. A single galaxy adrift in black. Then eventually only darkness itself. And yet there is a strange grace in knowing this. That we can stand on a small planet, scarcely 4.5 billion years old, predict the fates of things trillions of years from now, is itself extraordinary. Our theories of expansion, gravity, quantum physics let us look not just backward to the first light, but forward into deep time. When we speak of cosmic acceleration and heat death, we are translating silent physical laws into a story, one that stretches longer than stars can burn. The night we know now is full and alive compared to that remote age. Look up today and you see the light of Andromeda on its way to collide with the Milky Way in 4 billion years. The soft glow of galaxies billions of light years, distant ancient quasars, still whispering. The microwave background still hums faintly behind everything. We live at a fortunate moment when the past is visible and the great beyond has not yet slipped away. Future astronomers will have no such window. They will see only their own island and perhaps puzzle over why their measurements suggest a lonely, static space. Visualize the far end of time, one last solitary star. Perhaps a fading red dwarf orbiting quietly in the halo of Milkomeda, shedding light into an ocean of nothing. Around it may circle dead worlds or none at all. Its glow will reach no one. Even if a watcher existed, there would be nothing else to watch. The universe will not end in fire, but in absence, a cooling, emptying, silent night. That image, a single star in endless black, is haunting, but it also clarifies why our present moment matters. We can see and know so much because we arrived at a cosmic instant. When light still connects distant places, every graph we draw now, every map from Kobe to Planck to Desi, is not just science, but a record for an age that will not have this sky. The loneliness of the far future is a reminder. Our expanding universe is generous, but fleeting in what it reveals. We are temporary witnesses with an astonishing view, able to chart an ocean before its shores drift forever apart, for as long as humans have looked up. We have tried to find fixed points in the shifting night, small certainties we can use to chart our way across oceans and through life itself. The knowledge that the universe is expanding and that there may be no ultimate center or edge has only sharpened that need. We have always been wanderers, and wanderers require bearings. Even in a cosmos that refuses to give us a single axis or still point, we build our own anchors, patterns in the stars, instruments that translate position into safety, symbols that say, here is where you stand. Centuries before telescopes or rockets, the people of the Pacific were already masters of moving through emptiness. Polynesian navigators set out across thousands of miles of open water with no maps but what they carried in memory. They studied the night sky until it was a living chart, rising points of Arcturus, Altair, Canopus, the tilt of the Southern Cross, the subtle path of the Milky Way overhead. They noticed how swells wrapped around islands far beyond the horizon, how birds flew at certain angles near dawn, how color changed in deep water when land was near. These voyagers built stick charts of curved twigs and shells to mark wave interference patterns, not to carry on deck, but to memorize and then leave ashore. At sea they were guided only by eyes and inherited understanding, a mental map as vast and fluid as the ocean itself. Their achievement is astonishing. A civilization without metal or engines crossing the largest water planet known, creating connection between scattered islands that, to outsiders, seemed lost. That tradition whispers something important about our place in the expanding cosmos. Even when there is no edge, no clear marker of home, people can still orient themselves through patience and pattern. Later, European sailors brought sextants and chronometers, instruments that could turn the sky into a coordinate grid. With a sextant, a navigator could measure the angle of a star or the midday sun above the horizon, and with a precise clock set to Greenwich time, know latitude and eventually longitude. These tools were born from centuries of trial and error. John Harrison's clocks, the nautical almanac, the quiet work of calculating lunar distances. Each was an answer to the fear of being lost, to the knowledge that on an open ocean there is no natural boundary, only moving water and stars. Today's explorers push that same instinct further outward. On the International Space Station, astronauts travel at 28,000 kilometers per hour, circling Earth every 90 minutes. Their windows show a world without up or down, a planet that curves away in all directions. Yet inside the station, meaning is created through deliberate ritual and technology. Star trackers and gyroscopes know exactly where the craft is pointed. Screens glow with numbers describing position relative to the sun and the moon. Crews float, but keep careful logs. Draw lines on maps, and celebrate small anchors like shared meal times or the moment of orbital sunrise, which comes 16 times a day. The vastness outside would be disorienting without such markers. Astronomy itself is one of our deepest ways of anchoring. Even while it reveals how uncentered we are, it gives us constellations, cosmic addresses, and a language of belonging. We say we live on Earth, third planet of the Sun, a star in the Orion arm of the Milky Way. It's part of the local group, near the Virgo supercluster. These are man-made hierarchies, yet they help us feel placed. We name galaxies, chart their movement, turn raw expansion into maps and catalogs. The Sloan Digital Sky Survey built a three-dimensional atlas of 1,000,000 galaxies. DESI will push that to tens of millions. Each plotted is a reassurance. We may not have an edge, but we can know where we are relative to other lights. Even art and culture take up the task. Star maps have been painted on cave walls and cathedral ceilings, etched into Inuit tools, embroidered on sailors' clothes, and projected inside planetariums where children first learn the sky's stories. Ancient Chinese astronomers kept detailed charts, recording guest stars and novae. Mayan builders aligned temples to solstice sunrises. Islamic scholars refined celestial coordinates to guide prayer and travel. All of it is a response to motion and change, a way to say in a sea without shore, we will mark our passage. The expanding universe adds a new dimension to this search. We know now that the lights we use as guides are themselves in flight. Constellations deform slowly, but inexorably, as stars drift and galaxies rush apart. Yet even with this knowledge, we still build anchors, not by stopping motion, but by measuring it. We time pulsars, use quasars as reference beacons for spacecraft, lock deep space probes like Voyager onto a web of distant radio sources. The Deep Space Network listens to faint whispers billions of kilometers away and tells us exactly where our creations travel. When Voyager 1 turned back in 1990 and photographed the pale blue dot, it was not just taking a picture. It was saying that in this trackless ocean we can still know our place. Philosophers and poets do similar work in words. They take the unsettling fact of no center and turn it into something livable. Carl Sagan spoke of cosmic address as a form of humility, but also kinship. We are made of star stuff. Part of the same story as the galaxies fleeing at the edge of sight. Contemporary thinkers write of belonging not as fixed ground, but as participation. To be anchored is to be aware of motion. To accept that meaning is built, not given. The expansion becomes not erasure, but context. A vast sea in which our small marks matter because we choose them. It is striking how this impulse repeats across time. Polynesian navigators sailing by stars and swell, European sailors with sextants, modern astronauts with glowing tablets and gyroscopes, cosmologists drawing maps of hundreds of millions of galaxies, all are trying to say the same thing. We can live in a moving sea if we know how to look and measure. We can claim orientation even when there is no edge to stop us, standing outside under stars, where that space grows and will one day carry most galaxies beyond sight. The instinct to anchor does not fade. Instead, it grows more urgent. Our star charts, our long-distance spacecraft, our careful physics. Even the stories we tell children about the constellations. These are small ropes tied across an endless void. They may not hold forever, but they hold long enough for a life. Long enough to feel at home while the universe flows on. For more than a century, physicists have dreamed of listening to the universe in a way that goes beyond light. Light, no matter how deep we peer, can only show us what existed after the cosmos became transparent. About 380,000 years after the Big Bang. Before that, the young universe was a glowing fog of charged particles that scattered photons endlessly. Yet gravity, the bending and stretching of space itself, would have moved unhindered even through that first fire. If we could catch its faint ripples, we might touch a record older than any light can give us, direct whisper from creation's first heartbeat. This dream took an enormous step toward reality in 2015. When the twin LIGO detectors in the United States felt space itself ring, they were built with extraordinary delicacy. 4-kilometer vacuum tunnels laid in L-shapes in Louisiana and Washington. Lasers bouncing between mirrors polished to atomic smoothness. And systems tuned to notice distortions smaller than a proton's width. On September 14th of that year, signal swept through, a rising chirp lasting just a fraction of a second. Produced by two black holes spiraling together more than 1 billion light-years away. In that moment, Einstein's prediction from 1916 that gravity should travel as waves became something we could hear. The detection was a milestone, for the first time. Humans were not just watching the cosmos but feeling its fabric shiver since then. LIGO and its European partner Virgo have caught dozens of events. Black holes colliding, neutron stars smashing together, space groaning as it rearranges itself. Each detection expands our map of the invisible. When two neutron stars merged in August 2017, gravitational waves and light arrived together, letting astronomers test how fast gravity travels, exactly the speed of light. As relativity promised, and watch heavy elements like gold and platinum being forged in real time, this new astronomy is young but powerful, like the first scratchy radio signals once were. Yet the ambition does not stop at stellar cataclysms. Physicists want to push further back to the first instant of time, when inflation, that sudden breath that smoothed and stretched everything, might have stamped the universe with a background hum of gravitational waves. These would be unimaginably faint, a sea of ripples from the very birth of space. Detecting them would be a way to reach before the cosmic microwave background. Before any light at all, one approach is to study the microwave glow itself for subtle polarization patterns. As ancient light left the hot plasma, any passing gravitational waves from inflation would have twisted its polarization into a faint swirled pattern known as B-modes, telescopes at the South Pole and in Chile's Atacama Desert. Like BICEP and the Simons Observatory scan the sky for this delicate fingerprint. In 2014, there was excitement when BIP-2 announced a possible detection. Dust in our own galaxy turned out to mimic the signal. Still, the chase continues with better instruments. And future missions may yet tease out the telltale swirl. Another strategy is to build new detectors tuned for the long, slow waves that ground-based instruments cannot catch. LIGO and Virgo are limited by Earth's size and noise. They work best for cataclysms like black hole mergers, but not for the grand, stretched waves from inflation or orbiting supermassive black holes. To hear those scientists are designing LISA, the Laser Interferometer Space Antenna, is planned by the European Space Agency and NASA for the 2030s. LISA will be a triangle of 3 spacecraft millions of kilometers apart. Trailing Earth as it orbits the Sun, lasers will pass between them across empty space. And even the tiniest tremor in spacetime will shift the light's path. Freed from Earth's seismic and human noise, Lisa will listen to the universe's deep bass, the slow collisions of monster black holes, the combined chorus of countless binaries, and perhaps the relic waves of inflation itself. Thinking about this is humbling. Our species, just a few generations removed from sextants and paper star charts, is now trying to feel distortions in spacetime itself with tools of staggering precision. Each mirror suspended in vacuum, each photon traveling through those long arms, is part of an attempt to press our hands against the fabric and ask what lies beyond our current sight. And the stakes are enormous. If we can detect the faint gravitational background left from the first instant, we will learn how inflation really happened. Whether there were phase transitions in the newborn universe, perhaps even hints of other bubbles or exotic physics cannot reach with light. The technology itself is breathtaking but fragile. Lisa must hold its formation across millions of kilometers to within picometers. Its proof, masses must float perfectly free of any push but gravity. On Earth, next-generation projects like the Einstein Telescope in Europe and Cosmic Explorer in the United States plan to carve out even quieter, longer tunnels to push sensitivity further. Each new improvement turns the universe into a more detailed score, where black hole choirs and neutron star duets already play, and where the faint, ancient bassline might be waiting. There is a poetry to these efforts. Light gave us sight. Now gravity offers touch. When two black holes collide, the waves do not travel through something. They are the something. They are space, stretching, and relaxing as they pass. Our detectors sway ever so slightly, and in that sway we read stories from billions of years and billions of light years away. If inflation's whisper is caught, it will mean we have touched a moment so early it defies ordinary thought. A fraction of a second after time began. Picture it. In a quiet control room, scientists watch screens showing interference fringes, delicate stripes of laser light, and somewhere in those fringes is a tiny shift. One mirror moving less than the width of a proton. That shift means two holes bigger than suns have danced and died. Or someday, perhaps, it means we have felt the original shudder of creation itself. Lasers across voids, mirrors trembling to ghostly signals. These are the new telescopes. Even if the ultimate beyond remains unreachable, gravitational waves extend our reach in a profound way. They do not stop at surfaces of plasma or scatter like light. They carry news from places and times we could never otherwise know. As instruments grow, so does our ability to test ideas about what happened before the microwave background, about other bubbles, about dimensions that might flicker in and out at the universe's birth. We may never cross the horizon of our cosmic bubble, but we can feel its walls tremble, and in those tremors, perhaps learn what lies just outside our oldest light on a clear night. When the air is cool enough to sting a little, and the insects have gone quiet, you can still stand and look up just as people did long before telescopes or theories. The stars seem fixed and slow, and yet you know now that they are not still at all. The whole lattice of galaxies is drifting apart, the darkness between them growing deeper with every passing second. You may ask yourself, as countless others have asked, if everything is expanding, then what lies beyond? What does the universe expand into? The question feels natural, almost impossible not to ask. And yet it is one that slips away each time we try to hold it. Our minds want edges and containers. We know rivers flow into seas, rooms sit inside houses, and houses on land. So we imagine space itself must have an outside, something to push into. But the expansion of the universe is not like water spilling into emptiness. It is more like the stretching of the very fabric of reality, where the distance between points grows without there needing to be a larger arena. Mathematicians say space can be unbounded but without an exterior. Like the surface of a sphere with no edge, yet no outside in the two-dimensional sense. Cosmologists try to explain it with balloons and raisins, with grid lines on flexible sheets, but each analogy fails when pushed too far. We can chart the growth of distances, we can measure how fast, but we cannot point to a boundary or an external place. The night makes this both humbling and thrilling. Every photograph from Hubble or James Webb, every map of filaments and voids, Every ripple measured in the cosmic microwave background has carried us closer to understanding the geometry of all things. We know that galaxies are fleeing in every direction because space itself stretches. We know the universe is nearly flat, yet may still be curved beyond our reach. We know there is an observable limit, a horizon defined by the speed of light and the age of time. But we also know that beyond that horizon, space does not stop. It simply continues, perhaps forever, perhaps looping back on itself in ways we cannot picture. Some scientists suspect that our question about into what is itself misplaced, a relic of everyday experience trying to grapple with something stranger. If space is all there is, asking what it expands into may be like asking what lies north of the North Pole, but refusing to ask would feel wrong too. The drive to know has always pulled us further. From Polynesian wayfinders trusting star paths, to astronomers like Henrietta Leavitt finding cosmic yardsticks, to the engineers who built detectors that can feel black holes collide, each step came because someone dared to press a question that seemed almost nonsensical at first. There is wonder in the pursuit, even when the answer dissolves. A century ago, Edwin Hubble peered at smudges on glass plates at Mount Wilson, slowly realizing they were whole galaxies rushing away. His chalkboard plots shifted our cosmic self-image overnight. In 1964, Arno Penzias and Robert Wilson chased pigeons out of an antenna and stumbled on the Big Bang's faint echo. In 1998, teams using Type Ia supernova learned that expansion was accelerating, pending assumptions yet again. None of them set out thinking they would define the edge of everything. They followed curiosity and small anomalies until the horizon of knowledge moved. We are still doing it now. The James Webb Space Telescope reaches into the first few 100 million years, showing galaxies too grown for their age, hinting that our models of early growth need refining. LIGO and Virgo let us feel space ripple. Lisa will soon listen to deeper chords. Telescopes in polar deserts and mountain air measure the polarization of ancient light, chasing the first tremors of inflation itself. Each project is one more hand reaching for the invisible frame of existence. Even if we know the frame may not be real, there is also a quiet beauty in how humans make meaning along the way. Artists paint expansion as spirals and threads. Poets write of stars rushing into distance. Philosophers wrestle with the idea of no center. Astronauts aboard the International Space Station, circling the planet every 90 minutes, mark each dawn and dusk with care, even though space outside has no compass. We plant small flags of understanding in a sea that will not stop moving. Standing beneath the sky, you can feel both tiny and connected. The same physics that lets galaxies flee also lets you breathe and think. The same cosmic microwave background hums through your own atoms. You will not live to see galaxies slip beyond view, but you live at a moment when their light still arrives, when the record of the universe's birth is still accessible, when the tools to measure and wonder are alive. That is a rare gift, an accident of cosmic timing. Perhaps the question, what is it expanding into, will always remain partly unanswered, because space is not a balloon floating in some greater void. It is the totality of distance itself growing. But asking will always lead us somewhere worthwhile, to deeper theories, to better instruments, to more exquisite maps, and to a sharper sense of awe. The paradox is part of the point. We chase an answer knowing it may dissolve, but the chase itself builds bridges of understanding and wonder across the dark. So you stand there, maybe alone, maybe with someone beside you, breathing under the sweep of stars that have been racing outward for almost 14 billion years. Just enough to feel the depth of the mystery. You are on a small planet with fragile eyes and clever tools, yet capable of touching the fabric of spacetime and sensing its growth. And you know that while the edges remain beyond reach, the search itself is its own kind of anchoring, a way to belong in a universe without borders. To look into endless night and still feel, quietly but firmly, at home.